Okay, yeah, so hi everyone, like my name is Mark. I've been working on PyTorch core for about like 5 years now at Meta. So a lot of my work has been like really focused around like performance. But over the last 2 years or so, like the majority of my time has been going to like an open source like Discord community called GPU mode. And this is like honestly where I spend the vast majority of my time. So I feel like uniquely qualified to talk about like the role of like performance libraries and communities. All right. Okay, this is not working. I could go for a speech, but it might be challenging. It's like, okay, wonderful. Okay, no, again. Should I just use my laptop? Okay, this works, wonderful. Let's be here. All right, so last year, actually, I was like in the audience here. And it was like really nice because like Phil actually did give a big call out to, at the time what the community was called was CUDA mode. But what was interesting is that even though the community is called CUDA mode, we actually at the time had more people playing around with Triton than we did with CUDA. Like people would read the PMPP book, they're like, okay, cool, threads, UG, and then like tiles, they're like, yes, that makes sense. Like let me write my softmax, let me write my matmulls. And then people could ship stuff in real PyTorch code and things like really clicked. So I'm actually really grateful to Phil for plugging us. And he also like frequently shows up on the server to ask questions. And yeah, so this is kind of like the intro here, and I will sort of caution and say that, like, I think during the Q&A with Phil, I think Phil was saying something like, "Oh, the questions aren't spicy enough." I do feel like the role of an opening talk should be to like spur discussion. So I will say some unhinged things, like please forgive me, but hopefully it makes the discussion a bit more interesting. All right, let's get started. So yeah, I mean, like if you're curious about what GPU mode is, like it used to be called CUDA mode. It was a reading group for one of my colleagues, like Andrea Skopf and I, to learn CUDA. But it turned into like weekly lectures where we go over like different like GPU programming techniques. We have over 83 lectures, like 25,000 YouTube subscribers. We have a kernel competition platform where people compete on writing fast GPU code. We've seen over like 65,000 like submissions. That are all like basically redistributed under open license. For context, this is more than permissively licensed data that exists on all of GitHub combined. And we also have a chat room and working groups where basically people self-organize, like, and they build working groups together. And we have like really prominent alumni such as Karpathy's alum.c, Liger, which are like the last talk here today, and torch.io, which is another quantization library I personally worked on. All right. So yeah, I mean, we do like, so at the top left here, like this is our kernel competition platform. Like if you want to like learn about the talks, like they're here at the bottom left. We also do events. We're doing a big one here in SF on Friday with the theme being distributed compute. And that's like our YouTube at the bottom right. All right, so culturally, the reason why we found Triton interesting in our community and like why we aligned culturally is like there's a lot of mentions of Triton. It also shows up quite a bit in like the fastest entries on our kernel competitions. And a lot of our working groups basically were very much like Triton first, as in like there were things like Popcorn, which is like a kernel LM project like I worked on. You know, again, the goal was to get LMs to write Triton code. Torch.io, fundamentally a quantization library where you bit pack PyTorch code and then like code gen efficient Triton code using torch.compile. And then there was like some handwritten kernels we use like GemLite, which has like very fast like GemVs and gems. And then and Liger was probably one of our nicest successes. All right. So I don't know if people remember this, but like before, maybe like a week before Triton was like released in open source with that first OpenAI blog, there was like very much like this mindset in GPU programming of like you shouldn't reinvent the wheel, right? Like basically just use the library that the experts created. And because like GPUs are too complicated for us mere mortals, like we should just use like whatever higher level dependencies exist and just call it a day. But you know, I would posit that like reinventing the wheel is good because reinventing the wheel gives you the ability to understand how wheels work and then build better wheels. So again, this is why like we so culturally aligned with Triton because like it was like very much the opposite from what we'd heard from like other vendors like encouraging us to use their libraries. All right, so how do you make GPU programming more accessible? You know, one idea is you build better tools. Like Triton is like one great example. Like others are torch.compile, like slightly higher levels. But you know, my take on this was like, well, if you just make more people smarter at building GPU code, you're going to get like more GPU kernels. And if you do this in the open, that's great because like more of these kernels will be open source. People can learn. People are more likely to keep doing open source stuff as opposed to having like the fastest code be like gated somewhere, never to be seen again. All right. Okay. So I would still say though, like I think GPU programming, like despite like our volume, like GPU programming is still not mainstream. And kind of like the hill I'm willing to die on here is that like NCU is still not enabled by default on most like cloud vendors. Like if you try to run any NCU, you'll get like this like very ugly NGPU, CTR, perm error. You can't access hardware counters because security. But like it's really easy to enable this. Like you just like, you can just run this like options flag. You just like update like a conf file and you reboot your machine and great, and NCU works. I say this because like if you happen to be a cloud vendor or NeoCloud in the audience and you want me to give you a free advertisement, and if you can prove to me that you ran NCUs enabled by default, I will say that you're a great cloud vendor. So please reach out. All right. Okay, let's start talking a bit more about Triton. So again, like if you look at the impact, it wasn't like just the kernels. It's also like basically this like total domination of like the tile-based programming model. Like NVIDIA had like the tileless like level GPU kernel programming language. Like then Bryce, like one of the CUDA tech leads, like was also announcing like Qtile, which is like also another like array programming, like tile-based programming language. Jason's going to be talking about Helion, which is PyTorch with tiles. And then of course you have TileLang, which is the Lang of tiles. So like it seems like overall this has been a total cultural victory. And it's not just like even the programming model, it's even like the benchmarking tools. Like I just find it remarkable that this is like one of the functions I see the most in AI systems code. That like even if you're not running Triton code, like you just like run do bench and you get like measurements that like don't suck and are consistent and are stable. And this is, I think, like much better than what we historically do in PyTorch. And it's okay, I can make fun of PyTorch because I work on it, where we tell people like, oh, actually, you forgot to synchronize your code and you can't use time.time and you have to use CUDA events. And this is all like very dumb stuff, and we should just like all use do bench. Do bench is great. All right. So not only was it the programming model, not only was it the tooling and profiling, like this is like a total cultural victory, right? Like Phil, like not just the United States, like all of the world is now like building tile-based like GPU programming languages. It's used by tons of people. But like I think it's easy to sort of say this like in hindsight and say, okay, that's great, right? Like Phil's really smart, he figured it out. But I think it's like interesting to sort of like look back and try to figure out like what the Triton team did right that's not often expressed in these kinds of talks. Okay, so why did Triton succeed? I have like four takes on this. Like the first one is that the tile-based programming model was the right level of abstraction at the time. My second argument is that people like Python. The third one is people like PyTorch. And the last one is like advanced users could still squeeze out like some amount of perf. So I'll talk about like each of these. Okay, so I think I've seen Phil share some other version of this slide a lot. Like he has like the curve like bending with productivity. The way I like to think of it is a bit different. Like I would encourage you to read this picture going from math all the way to like the PTX section. Math is great because math is infinitely backwards compatible. Like the torch.compile algorithm will almost never change. Like the world will end and we'll still have like matrix multiplications be relevant. The way I think about PyTorch is that like it maximizes researcher productivity. If it maximizes perf as well, that's kind of considered a cherry on top, but it's not like the goal. Helion basically is now like somewhere close to PyTorch. Like I think of it like Triton, but with more auto-tuning. Triton is, of course, like the OG tile-based programming language. And then, at the lower level, when we get to more like native languages, you have thunderkittens, which I call like Cutlass, but easy to read. Then you have Cutlass, which is very fast matmls. CUDA, which I think very few people actually program like raw CUDA anymore. It's like more helpful for surgical improvements as opposed to rewriting your whole model, kind of like LMLC. And PTX, of course, is even more surgical. So, all right. So let's talk about math, right? So I mentioned that the API is completely backwards compatible. So it's been backwards compatible since 1812. So the inventor was another Frenchman, so they seem to be really attached to the matrix multiplication algorithm. And so yeah, basically, like the nice thing about this function is it has two arguments, like A and B, and it just outputs like a C, like a third tensor. But most importantly, it doesn't describe how the computation is done. So notice there's no things like the tiles or auto-tuning. Like it just describes like what the computation is. If you go to PyTorch, it's actually not too different, right? So PyTorch, for example, takes an input and another. So this is the A and B, and then an optional out tensor, because you can also in-place things. And it needs like a lot more thought, like basically. But however, PyTorch developers now, basically the burden on making this run fast is on PyTorch developers. Like basically, we need to think, okay, you are running on like this device or this accelerator using this D type, and this is the kind of tensor you have. And we go through a giant dispatch table, and we spit out like a kernel that is performant. So you can think of it like a giant like lookup table towards like finding a performant kernel. So this is kind of what makes Triton interesting. Like for the Triton does not actually have like an MM function, right? Like Triton actually makes you think about like the computation you're doing. You have to think about like tiles, and you have like parameters and blocks and group size that you need to change. You might need to change like this like long list of like configs to get like decent perf. There's a lot of bound checking code, and there's pointers even though we're in Python. Like what's going on, right? But the benefit is like it sort of offloads all of this responsibility onto the user, but now you get perfect control over what gets fused. Like you know that if you're writing a Triton function and there's like two like mathematical operations that are under the same like Triton.decorator, like they will get fused, and this is like a very, very nice guarantee, even for compiler people that want to spit out like Triton code, right? So, okay, so moving on, like I made the claim that people like Triton because people like Python, right? But you know, it sort of looks like Python, but like, is it really? Like, I mean, does like my Python, like I'm a Python programmer, like I basically know for loops, lists, and dicts. It's like this is the extent of my data structure knowledge. But here there's like a lot more stuff, right? Like there's this like program ID, okay, and then there's this like weird broadcasting. There's this like weird masking using like comparison offs. There's like pointers and offsets. If you add print statements, it wouldn't work. If you had a debug statement, like it wouldn't work either. So it's not really Python code. It just like looks like Python code that you can put in a Python file. So what do I mean when I say people like Python code if they like Triton? So what I mean is that people don't like C++. And specifically, when I say that people don't like C++, it's to be very specific. There's like the syntax. Okay, it's easy to make fun of it. So this we know. So I won't sort of elaborate the point. The other one is like C++ also has like this like extra overhead, as in like you need to learn about like make files, and then you have to PyBind your function to add it to a PyTorch program, and now you have to marshal a pointer and turn it into a tensor with the right strides. Otherwise, you get an IMA. You know, you're like, oh, like we couldn't figure out like how to add this like C++ dependency because like NVRTC isn't completely documented with like which libraries you can link versus not, and so you kind of like have to sort of like guess or just use NVCC that has like painfully long compile times that can range on the order of like 90 seconds. And then, you know, once you get to shipping C++ code, like this is a huge pet peeve of mine. Like basically, why do people hate installing Xformers? Why do people hate installing Flash Attention 2? Well, because like this is the totally reasonable state of affairs of shipping C++ code today. So basically the way it works is that if you're shipping native code within a Python program, you need to fix the cross product of your Python version, your PyTorch version, your CUDA version, and your accelerator. So let's say there's like 3 choices for each of these. So you're basically doing like 3 times 4. So now you're like shipping 12 different binaries. And no one really wants to ship 12 binaries because now you have like these very complicated GitHub actions with the matrices and stuff. And so what you end up doing is you tell people install things from source. But if you tell people install things from source, well, compiling CUDA programs is really slow, unless you have a machine with like 128 cores, which like most people don't, right? And so then it like just like hangs because it's too slow. And this is like overall like a very unpleasant experience. It is getting better though. Like PyTorch did introduce ABI stability, so we can basically just like remove the PyTorch version from this equation, but it only basically divides the number of binaries we need to ship by maybe 2 or 3. So it's still like not a total victory. Okay. So really the point here is that like it's not like the fact that it's like Python, it's like the fact that it's easy to ship and that it's JITted. So PyTorch, for instance, has like a couple of popular functions called load and line. And there's like another one called compile kernel as well, which basically, the way all of these functions work is you can pass them as a string a bunch of like CUDA code, native code, and we'll automatically create like the right make files for you, we'll PyBind them for you, and like then it just like works, and then you can make it a custom operator so that it works with torch.compile and stuff like that. So this is trivial to package because you're not shipping a binary, you're shipping a string, right? So that if you don't like that the string is in line in the file, you can put it in a separate file. But at the same time, like the con here is like, of course, compilation time and surprising behavior, as in like you don't know what the behavior you're gonna get, you observe, until you actually like actually compile this kernel in prod, which if you care about numerics or if you're like an AGI lab, it's like it's kind of a hard sell. But hey, like the convenience of JITs like seems to sort of like win off in this trade-off. So like my hot take is the following. Like my hot take is because like Triton isn't really Python, that like the specific semantics of the DSL don't matter too much. So like whether this looked more like C++ code, whether it looked more like assembly or more like Mojo, I think these are like mostly aesthetic differences, because your boundary is often like a kernel that you're calling, and then you're binding it within a specific PyTorch program. All right. So here's a couple of things that, like, if you're a kernel DSL author in the audience, I would encourage you to sort of think about these things. So this is like a very simple PyTorch program that's calling like a Triton kernel. There's like a lot of clever things Triton does like very invisibly to sort of be PyTorch native. So the first one is here at the top. When you're calling an add kernel, it takes in as a flag like this X pointer. But like if you look at the actual kernel, like X is just like a tensor, right? So there's no like DL pack. There's no let me manually read a blob of memory and reconstruct a tensor with the right strides and maybe do it incorrectly. So this just makes things really convenient. The other one is that, like, again, if you're using Triton, if you're like whatever CUDA stream you're using in PyTorch, like Triton will reuse that. And whatever like device you're using to allocate your tensors, Triton will use that for the compute. And these are the kinds of things that in other kernel DSLs I find myself explicitly having to think about. That just like adds a level of clunkiness that's unnecessary. All right. So yeah, I mean, and PyTorch, like for what it's worth, like finds Triton like fairly convenient to work with. So for instance, like when people were first learning Triton, like about like a year and a half ago, there was this flag that people really liked called torch logs. So you could say like torch logs, output code, and then like have your Python train.py. The benefit of this is that you could compile a specific piece of PyTorch code and then get like what the Triton code would look like for it. So for example, like if you're compiling torch.square, you have like a bunch of loading and masking, but hey, like this is your square operation. That's like the temp1 equals temp0 times temp0. And if you're squaring twice, then it's the same thing, but now you're like basically multiplying temp1 by itself like twice. The nice thing, you look at this, well, the things that are under the same decorator, that's the same kernel, so you know that they're definitionally fused. And again, people really like this to learn Triton. Like, it was like very convenient. And the trick often I saw people using was they would like take a kernel like this, and then they would like ask ChatGPT to be like, please make this Triton kernel look human readable. And you get like something that looks like somewhat reasonable, because this obviously looks compiler generated. All right. So this sort of brings me to this like often this point, and I think maybe this like it's a kind of like an old ideological point that's like a bit moot, but like it was a debate I remember having a lot with people where it's like, oh, should I use Triton versus torch.compile? And I often found this question to be very ill-defined. And so, for instance, if you care about like a very specific kernel fusion to be done, you should use Triton. You want like a guarantee that these two operations will be fused. If all you care about is performance, you should use torch.compile, because like it's like the lowest effort technology that exists in the world to make like your models faster. Concretely, torch.compile uses Triton because, again, torch.compile needs to have a guarantee on what will get fused or not. So like because it needs these specific guarantees, it can like spit things in a Triton, it can spit like Triton code in a file, and things like just work fast. All right. So this is like basically my take as to what I think Triton did right to basically conquer the world. And I kind of want to briefly talk about like some projects that I really like that aren't giving talks today that I think should help you think about like what are important things people are building in Triton. All right. So the first one that I thought was kind of clever, I think I saw Horace somewhere in the room, but like flex attention. So what kind of makes flex attention interesting is at some point we did a crawl at Meta of all the Triton code that people have written on GitHub. It's pretty interesting. Like basically you have about 30% of all of the Triton code on GitHub is some attention variant. So like, I don't know if this is how Horace developed flex attention, probably not. But like one way of developing it would be like, oh, like a lot of people are doing this. How can I abstract it away and like make people write less code? There's a lot of other stuff like, like worst versions of what exists on the tutorials as well. But for the most part, like I said, like the sort of building nice abstractions on top of Triton, I think has something that like has been very fruitful for the community. The other one that I find interesting, which is basically, and I think it sort of touched on some of the earlier questions I heard, basically around like what PRs will Phil accept. A project that I found very interesting is like there's like this very like heated issue on Triton. I forget if it's closed because it's too heated at this point around having Windows support for Triton. And what I found kind of remarkable is like there was this one contributor who shows up a lot on GPU mode that's been at this point maintaining a Windows fork for over a year. And I think this is great. Like the fact that this is even possible for people to host backends out of core is great. I honestly think it's quite hard to support Windows really well. Even we run into these struggles in PyTorch where like, NAND semantics are different on Windows versus Linux. Like float 32s mean different things. And so like there's sort of like a lot of guns, and unless someone really deeply cares about Windows, you basically end up with like an in-core backend that's slop, and that's like not great for everyone. So I think these out-of-core backends can actually be more stable and better. The other one is like obviously like if we want like a kernel programming language that helps people make people more productive, the thesis cannot be there are 5 important kernels that should be accelerated. Like in that worldview, you just want to like write like PTX, right? So some work I really like is like work by Songlin, who's I believe now at like at Thinking, where she has like a couple of like a large, not a couple, like a very large volume of linear like attention variants for like basically efficient alternatives to attention. And this is like very much like an example where the 80-20 rule really matters. Like basically just like being able to churn out like large volumes of kernel that are like within like 10% or 20% of speed of light is just so much more important than having like 1 or 2 kernels that are at speed of light. Another project I really like that I think should be extended on is GemLight. So GemLight is, the main creator of this is like MobiCham. I didn't see him here today, but so he primarily conceived of like GemLight as a repository for low-bit gems and GemVs that are very useful for LLM decoding. So they're quite fast. He basically has like all the variants, like all the D types, all the activation sizes. And I suspect basically a project that takes this idea and turns it into like a low-bit gem zoo with some fused epilogues to be like very popular, because again, it makes like very specific guarantees around what gets fused. And I suspect something like this will be quite popular. So if you're interested in working on something like this, please talk to me after. I'd love to work with you. All right. The other one is like, there's a lot of benefits to popularity. And what I mean by this is that like earlier this year, I was like working a bunch on getting LLMs to generate very fast like Triton code. And if we looked at GitHub, there's not enough. Like we found like maybe about like 1,000 or 1,500 Triton kernels that are usable. But we found a lot more PyTorch programs that were usable. We found about 18,000 that we could run and didn't crash. So if you torch compile them with torch output, with torch logs output code, now you get pairs of PyTorch code to Triton code, and you can train a translation model. But again, the data here still looks compiler generated. So if you look at the early kernel LLM work that we did, the model was better than even like DeepSeek at like an 8B model is even better at DeepSeek at writing kernels. However, the kernels look compiler generated, and it's not kind of like what you would expect a human to write. So again, back to this popularity angle. How do we get more high quality Triton kernels on the public internet? And this is kind of like when we conceived of like kernel competitions. So as part of the benefit of GPU mode is like we have a very large audience, like around like 21,000 people. And we've hosted so far like 4 different kernel competitions. So the idea is you have a reference program in PyTorch, and then you need to write like a faster implementation of it. And the language doesn't matter. It could be Qt, it could be Triton, it could be CUDA, like it could be HIP, doesn't matter. We did like an intro-level problems with the PNPP textbook inspired problems. And then we very quickly followed up with 2 different problem sets that had a 100K prize pool. Some were basically inspired by like the DeepSeek kernels. The others were like basically kernels that like include comms that are popular in MOEs. We have an NVIDIA competition like coming up soon as well. And this is like very much like one of those things where like, again, it's a very efficient data aggregator. If you give a nice prize pool and you have interesting problems, you can get more data than you might organically get by the sort of diffusion process of open source. So if you're a company and there's like a couple of kernels you want to make faster, please reach out. We'd love to work with you. So one I'd like to call out, for example, is like we had this like smaller problem set called the trimal problem. So trimal is like a very nasty problem because you basically have like these 2 matmuls that you're doing with like some nonlinearity, and then you're doing like another matmul. A lot of compilers like sort of like fall flat on their face here. We very much also expected the faster implementations here to be something written in like low-level CUDA, but turns out like the fastest entry by David Barrar was actually written in Triton. And so like, because like the core trick was just being able to like change like memory layouts and not like other sort of details. Yeah. So the other one, which was like a bit more ambitious, was like we wanted to do like a distributed kernel competition. So basically we had like 3 problems, like all-to-all, like a fused like gem-reduced scatter, and a fused all-gather and gem. And what I found very interesting about like all of the winners here is basically the top team used mostly Triton. They only used HIP on one project where they were 3rd instead of winning. So Triton really was responsible here and helped them like get the best things, and things just composed. Like basically, as in, if you look at the gem-reduced scatter example, there was HIP code, but there was also Triton code, because a natural boundary for composability is the kernel, right? Like a different, like you don't need a kernel that like intersperses both. Each kernel can be written in whatever language you want. So I'm running out of time, so I'll just also say that like there's a lot of interesting excitement around distributed kernels in general. There's a lot of projects that I think are worth checking out. I think it's going to be a very active space. I know Wenlei is going to be giving a talk about Triton distributed later today. So this is like one of those things where I think you know, the winner is still unclear, but I think it's going to be very exciting. And sort of the last hot take I'll leave before questions, which is that like I also noticed in Q&A, a lot of people seem kind of upset at Gluon. It's like the questions weren't upset. They were more like, do you foresee the 2 things will compose? And like, why do we have 2 different programming models? And I kind of want to sort of encourage people to sort of say that like, hey, like modern kernels today are really complicated to write, and they look more like scheduling to code. It's okay if there's multiple kernel languages, because each kernel can be written in its own language. Like things don't need to compose more than that, so it's fine. I can say for myself and for a lot of people on GPU mode, we don't really want like another slow GPU programming language. We have a lot of those already. No one uses them. It's okay. They're nice, but you know, that's it. And I would say like it's generally okay to deprioritize performance, like portability, just for a little while. But you know, please keep performance portability in the back of your mind for like the right time to retackle this problem. So yeah, that's it for me. Thank you. I'd love to take questions. Yes, hello.
Yeah. Hey, Mark, great talk. I have a slightly spicy question.
Tell me, yes.
You mentioned that when you were talking about why Triton was successful, that tile-based abstraction was the right abstraction at that time. So I was wondering why you qualified it that way. Do you still think with the hindsight that it's still the right level of abstraction to target?
Yeah, like I think often when thinking about these decisions, like the dimension of time is really important. Like basically, you know, if Gluon came out like 2 years ago, I'm not sure it would have been like that impactful of a project. But I think it's coming up at the right time when like people really care about Blockfootwell performance, and the MFUs people are getting aren't like very, very good. So I think it's fine, because like it's one of those things like, you know, you want Triton, you want the large community, you want the platform, you want like sort of get developers with you, and then it's much easier to introduce lower level languages. For what it's worth, I've also noticed in GPU mode, like the community has gotten less newbie over time. Like, you know, when we started 2 years ago, it was like very much like, oh, like we're reading textbooks, and now people are writing like state-of-the-art comps kernels. So I think it's okay if the tools evolve to cater for advanced users over time. Yeah.
Thank you.
Yeah, Daniel's probably going to ask me a spicy question.
You mentioned a lot of interest in distributed kernels, and I was lucky enough to be at the GPU mode hackathon literally 12 months ago. And there was one project on implementing Nickel and Triton.
Tickle, yes.
Tickle, yeah.
Yes.
And now you showed maybe 8 separate projects.
Yes.
That I don't know what they're based in, but do you have any thoughts on how in the span of 12 months, you know, literally everyone's like, oh, you can't re-implement Nickel, it's too complicated, and now we have this?
I mean, skill issue, I don't know. It's like, but I mean, no, like less joking. Like, I think a lot of it is like you get like sort of brilliant people that pop their head in open source and disappear. So I think Tickle was initially a fork of like Yifu's symmetric memory recipes. Yifu went to thinking machines and he disappeared. And then like Clive, I think later went to OpenAI. So then again, like Clive disappeared. We don't know what's going to happen with Tickle. So I think like these early recipes were maybe like good evidence that like these ideas aren't as crazy as people thought. And it's like one of those things where like maybe I suspect like for, for the first person, like Yifu, like it required like sort of a lot of like boldness to say, no, I think this is fine, we can do this. But I think for everyone that comes after, well, it's been proven out. So now like the problems are a bit different. Like you're not trying to say whether something's possible. You're trying to convince that like the integrations are good, that the performance portability is good, that the binaries aren't miserable to install, that the examples actually work. So the problems evolve a bit more. But yeah, I think a lot of it is like thanks to the early work of Yifu.
Thank you.
All right, I think we're
thank you.
at time. Let's thank Mark again for a fantastic talk.
Thank you so much.
Thank you, sir. Actually, Mark, maybe as they're setting up the laptop for the next next one, I can ask another question.
Tell me, yes.
So as the GPU mode guy, what do you think are the most important activities that we could do to increase the community and the engagement? Is it these hackathons, or are there other things that we should be focusing on as a community to get more people in?
Yeah, like, I mean, I would say that there's like a few things. Like, I think generally when people think of community, I think people think of it somewhat shallowly, where they go like, I did this thing, and now I just need to tell people about the thing, and this is community. My general sense of it is you want like technologies that are like amenable for people to graduate from a like user to contributor like fairly well, which is why like I think working groups that like sort of say something like, hey, like there's this interesting feature we want to build in Triton, like let's say Proton for me is like a perfect example. Like we all love profilers. Like can we basically build it more in public and have the meetings happen in public? And similarly, I think if there's advanced features that people want to know about, can we encourage people to use them in kernel leaderboards, for example? So those would be my two big ones.
All right. Thanks again. Let's thank Mark one last time for a great talk. Thank you very much.